To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Werner von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would be the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that men can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model I designed for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel, and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the 4th stage. This would also give the crew more and more training. Following that, the 3rd and 2nd stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge 1st stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space. Let's look ahead a few years and see how this might be accomplished.